Okay, so that's recording. So can you guys keep the your cameras on so I can see that there's people here? So I know I'm still connected and not talking to the wall. Um, and I will switch to my iPad and let me know if something weird goes on with the broadcast. Okay, so. So last week, what we did, I'm going to just tell. So last week, what we did, we looked mostly at the topological excitations of a superfluid, and we saw, in fact, how superfluidity arises. The sort of quote lack of viscosity is actually not really that at all, but is something that emerges from the existence of a microscopically occupied quantum state. So at the end of last time, we started to talk about this week's topic, which is quasi-particles. And so the idea is, how do we deal with a strongly interacting system when we can't really do calculations systematically? And what we talked about was the idea of a quasi-particle. And the idea of a quasi-particle was that you have excitations that behave like free particles, as shown here on the top right-hand side of the screen. So here we have the energy of the system now written down as some ground state plus the energy of quasi-particles. So these are states that are occupied by a certain number of these quasi-particles. That's n of p. Each of these quasi-particles is supposed to have an energy spectrum or dispersion relation, which is the energy for each particle as a function of momentum p. So that's written down as the second term. And the key point is that these particles are supposed to be, to a first approximation, non-interacting. And because they're non-interacting, then we can do some calculation about them to do with their properties. So the idea is that the E naught is just the energy of the ground state of the system, and then the quasi-particles describe the excitations. And even though in general we can't calculate the ground state of a many-body system, we can calculate something to do with the energy spectrum, or at least hypothesize about it. Now, this whole idea came about due to Landau, and he used it, as we'll see in a few minutes, to explain the heat capacity of superfluid helium-4 in the 1940s. Now, he just sort of guessed it, and we'll come to that in a minute. But and of course, it's far from obvious that this idea is true, and no reason why one should expect it to be. But in fact, it turns out that one can actually derive it. And the person who derived it was Landau's arch enemy, Bogolyubov, Nikolai Bogolyubov, and that's how we're going to approach this problem. So what we're going to do today is this is the lecture from hell, or perhaps the lecture from helium-2. So we're going to talk about quasi-particles. We're going to first of all see that start off by commenting that ideal bosons undergo Bose-Einstein condensation, and that gives them a macroscopic quantum state. But this state does not itself exhibit superfluidity. And why that's the case, I'm not going to tell you today. I will refer to that a little bit later. But if you want to understand this, you can look at section 3.2 of the notes. So basically, the whole notion of superfluidity has in it an upper critical velocity. And if the speed of the flow exceeds that flow, then superfluidity vanishes. And he even made this argument based on kinematics, and we'll talk about it a little bit later. It's not a complete theory for superfluidity, but what we'll see, in fact, is that a non-interacting Bose-Einstein condensator is not really a superfluid, because the minute you try to move it, it gets some dissipation. So we're forced to then look at interacting Bose systems like superfluid helium or like the quantum cold atom gases, and that's what we're going to be doing today. Conceptually, it involves a lot of algebra, and you definitely won't be able to follow it all in real time. It seems simple, but actually it is very sophisticated, and in fact, I would say it's still not fully understood in all its ramifications. This method is the reason I'm teaching to you is that it is a paradigm for doing complex interacting systems, and so it does have a wider validity beyond the situation that we're going to describe here. Okay, so let's get started. Section 3.1.1. What I've sketched here already is the excitation spectrum of helium-2. Now, this is the excitation spectrum as Landau guessed it in the 1940s, but it's also been experimentally measured, and it was measured about 15 years after he made the prediction using neutron scattering, and it basically turned out to be amazingly correct. So what you can see I'm plotting here is wave number. So wave number along the horizontal axis and excitation energy divided by Boltzmann's constant on the vertical axis. So the vertical axis is essentially in units of temperature. And what you can see is that the low wave numbers, long wavelengths, the energy spectrum has a straight line form, which I've indicated is called a phonon. So epsilon goes as h bar c1k, where c1 is the speed of first sound. And then there's a minimum at a wave number k naught, which is close to 2 times 10 to the 8 inverse centimeters. And that minimum is called the Roton minimum. And people thought originally that this was related to some sort of rotatory motions or whatever, but in fact that's not really correct. It's just some excitation aspect of the excitations of the system. And what Landau did, I'm not going to go into full detail and show you the calculation, but what he did was he assumed this form of the spectrum, calculated the heat capacity, and showed that this form of the spectrum explained the heat capacity as a function of temperature that was experimentally determined. Okay, so that was Landau's brilliant idea, and it was very important. And now what we're going to do is work out how something like this can be understood mathematically. So helium-4, of course, is a strongly interacting dense Bose fluid. So what we're going to do is, in fact, do a calculation for weakly interacting bosons. So here we go. So we're going to start off with the interaction energy, U of Ri minus Rj. So that's the potential energy between two bosons at Ri and Rj. We write down the Hamiltonian for this, the kinetic energy plus the potential energy. And we've got this 1/2 in front of the potential energy because when atom 1 interacts with atom 3, that's the same as atom 3 interacting with atom 1. And so we don't overcount, and so we divide by 2. Now we're going to transform this form of the potential energy into the microscopic density operator of the system. So we define the microscopic density by writing down rho as the sum of delta functions centered at the positions of each of the particles. So over here on the right-hand side, you can see that I've drawn a box with a bunch of bosons sitting inside it. Now these represent the positions of the particles, and so we put a delta function at each particle. So if we integrate this rho of r over some particular volume, it will tell us what is the number of particles in that volume. And so that's why we call it the density. And so then if you want to work out what does the potential energy of the system look like, well, the potential energy of the system is just sum of ij, u of Ri minus Rj, and that is just the integral over this microscopic density, rho of r prime, u of r minus r prime. Okay, so that's our starting point, and then we're also going to write down the kinetic energy of the system. So the bosons have a potential energy which I can write as H is the sum over wave numbers over K, and then H bar squared over 2m K squared times the number of bosons at that wave number K. So that's the kinetic energy. And N of K, I'm going to write in terms of annihilation and creation operators as a K dagger, AK. Okay, so everybody happy with this as my starting point? Any questions?
Yes. So for the calculation of the potential energy, should we exclude I equals J, the terms for I equals J?
Yes, we should, and we'll talk about that in just a minute. So I'll come to that. Thank you. Okay, any other questions? Okay, so let's carry on with the calculation. So before we've written down what AK and A dagger mean. So let me just write that down very quickly. So AK dagger acts on a state with N1 up to NK. These label the occupation numbers of different wave number states, and this is a creation operator. So it creates a state, it creates an extra particle in the state K. So this then looks like N1 up to NK now has another particle in it, and that's what the annihilation operator, the creation operator does. Similarly, the annihilation operator acting on this state will give us one less particle in the state K. So that's the usual operator identities, and these annihilation and creation operators obey the usual annihilation and creation operator commutation relations. A K dagger prime is equal to delta of K prime, and and then the annihilation operators acting with themselves commute, and same with the creation operators. Okay, so that's the setup, and the plane the wave function that these create plane wave states. Which I could write as 1 over the square root of V e to the I K dot Ri. So if you wanted to know, or actually just R, so if you wanted to know what wave function is created by the system, this would be the wave functions that correspond to these states. Okay, so I want to now talk about field operators. So again, I want to emphasize to those who came late, I want you to just follow along the logic. Don't try to follow all the mathematics or the algebra. You can follow that on later, and if you have any questions, I can explain it to you. So now we're going to write down field operators. And these just create and annihilate particles in real space. So I'll write these down in the following way. Psi of r is equal to 1 over the square root of v, sum of k, e to the I, k dot r, a k, and psi dagger of r is 1 over the square root of v, sum over k, e to the minus I, k dot r, a k dagger. And these things then commute. So psi of r prime equals the same thing with daggers is equal to 0, and psi of r prime dagger is equal to delta of r minus r prime. And if you want, you can go and compute those things from the definitions. And if I want to work out what is the density at any given point, so this is the microscopic density operator, this thing is just psi dagger of r, psi of r. And this is proved in the lecture notes, so I'm not going to do it in class. So for the proof, see equations 3.70 onwards. So there's a fairly long discussion up to about 3.76, and the end result is that you derive that this is true, and this rho of r is equal to sum over I equals 1 to n delta of r minus ri, where the ri is really the operator corresponding to the particle positions. Okay, so that's the density. So the number operator is then the integral over all space psi of r, and this is psi dagger. So this is the total number of particles in my system V. All right, so then let's just remind ourselves what our Fourier transform variable is. So we're going to define Fourier transforms in the following way. So I'll call it f of k is equal to the integral d3r e to the minus I k dot r, f of r, and f of r is equal to then 1 over v sum over k f filled over k e to the I k dot r. So that's how I define Fourier transform. Okay, so next question. Again, don't try to follow this. Let me write down what is the Fourier transform of the density. So you can check this. If I take the density operator and take its Fourier transform, so I get the Fourier transform k-space, it looks like this. It's obvious that it's going to involve an A dagger and an A, because the density involves psi dagger and psi, the number operator involves A dagger and A, so it's going to look something like that. It's also going to involve K, but there's what you may not have had guessed is that it looks like this. It looks like this. So there is a dummy variable here, summing over Q. So there is our Q. And then the variable on the left-hand side is a function of K. And so that's where the K comes in. So that's what this object is. And why is this important? Well, what we want to work out is the form for the energy of the system. So what we're going to use this to express the energy of the system in terms of annihilation and creation operators. In particular, we're going to express the potential energy. So why do we want to do that? Well, back over here on the left-hand side of the screen, we have the kinetic energy is written down in terms of the annihilation creation operators. The potential energy is written down in terms of an integral over real space. And so what we want to do is turn it into an integral over annihilation creation operators. So we're going to do that. So if I work out the potential energy, the interaction energy of the system, so I'll call that H interaction, and that has the following form. I'll write it down and then just make a comment. So it's going to look like this. It's going to look like 1 over 2v, sum over k, then u of k, a rho of k, rho minus k. So that's what it turns out to be, and you can see why it's going to look something like that, because if I look back over here on the left-hand side of the screen, rho of r prime, u of r minus r prime, that has the form of convolution, and so you know it's going to be just a sum over k modes in momentum space. Okay, well, we know what rho of k is in terms of annihilation and creation operators, so I can write that down now in terms of annihilation and creation operators. So I can write it down over here. So this is going to be 1 over 2v, the sum over k, and then there's going to be some dummy variables. So I'll call those q and q prime, and then I have u tilde of k, the Fourier transform of the interaction potential, times this a k plus q dagger a q, and then a q prime minus k dagger a q prime. So that's the interaction form for the energy. And if we could just leave it like that and calculate, but if we did, we'd be making a terrible mistake. So now I'm going to make a comment about the nature of this. And in order to explain this, what we're going to do is we're going to remind ourselves that that these operators are non-commuting, and in particular, if I look at the term AQ, AQ times AQ prime minus K dagger. So this is the term that's in the middle here. So this term is just equal to, if I commute the operators past each other, so this is A dagger Q prime minus K A Q. So I've swapped the order of them, and then I have to insert the commutator. So that is going to be delta of Q prime minus K. So what I've done is I've swapped around AQ and AQ prime minus K, and in doing so, I just use the fact that those things can have the commuter as shown over here. Okay, so why am I doing this? Well, let's now then rewrite our interaction Hamiltonian. So our interaction Hamiltonian now looks like this. It looks like 1 over 2v, and then the sum over k, q, and Q prime, U tilde of K, and now it looks like this, A, K plus Q, dagger, A, Q prime minus K, dagger, A, Q, A, Q prime. So that's the first term, but there's another term because I have this this delta function over here. So this term is now going to make is going to add another contribution to the right-hand side. So I'm going to write that down as follows. That's going to be 1 over 2v, and then it's going to be sum over k, u tilde of k times the sum over q prime of a q prime dagger a q prime. Okay, so all I've done there is I've substituted the term outlined in brown into the formula up here, and that's going to give you this extra term over here. So this term over here corresponds to all of this. So now if you look at this term, well, this term is just the number operator. So this is just the total number of particles in the system. And this term over here, the sum over u of k, well, that looks a little bit weird until you remember that the way I've defined a Fourier transform is over here. I've indicated it on the left with a star. So if I set r equals 0, then I get sum over k f tilde of k. So this term over here actually is nothing more than 1/2 the potential at its origin, r equals 0, and then multiplied by n. Okay, so this should be very worrying to you, because usually the potential, like say a Lennard-Jones potential or a Coulomb potential and so on, so usually this is usually divergent. So if I plot u as a function of r for the usual pair potential, so u at the origin is usually infinity, and so that means that this term over here is infinity. Okay, so that's terrible. So, but we say, well, okay, that's fine. So why don't we just do this? Let's simply change our zero of energy. So what we're going to do is we're going to make our zero of energy change. So our Hamiltonian is going to be what we had before. So I'll call that our old Hamiltonian. And then I'm just going to simply subtract off minus 1/2 u at r equals 0 times n. And then if I do that, then my Hamiltonian now becomes something much simpler. So it's h bar squared k squared over 2m, ak dagger ak, so that's the kinetic energy, and then the potential energy term now looks like this. I'm going to write it in the following form: k1, k2, k3, k4. It's going to depend on u tilde of k1 minus k3, and then the important point is that it looks like this. That's a k1 dagger, a k2 dagger, a K3, a K4. So there's that multiplied by a delta function, K1 plus K2, K3 plus K4. So this is a momentum conserving delta function. And all I've done here is I substituted into the expression I have on the previous page, and then I just redefined my Ks and K1s and K2s and so on, so that it has this very nice symmetric form. What you can see is that we have in this form of the potential, this form of the potential has all the creation operators to the left of all the annihilation operators. And the people who do quantum field theory, they call this normal ordering. And they don't really say what is the reason for it, but now we can see what the real reason is. So what is the reason for this? And the answer is that what we've done is we've written that the potential energy of the system is U. We wrote this down like this. That's how we wrote it before, but actually, so I can think of this as being the sum over I not equal to J of U of Ri minus Rj plus the sum when I equals J of U of R minus Rj, and that is equal to the sum from I not equal to J of U of Ri minus Rj plus, and then each of these terms on the right-hand side over here, when I equals J, this is U at R equals 0. And how many of them are there? Well, there are n of those. And so what we have is n times U at R equals 0. And so what we've done by subtracting this term, so by doing normal ordering, we've just subtracted out each particle's self-interaction. So in other words, this Hamiltonian that we've written down is nothing more than the sum over the kinetic energy, Pi squared, plus 1/2 the sum of I not equal to J of U of Ri minus Rj. So what we've done by doing this is we've been able to find a way to write down this Hamiltonian without the self-interaction in terms of annihilation creation operators. So let me just pause there and see if anybody has a question about this. So I spent a long time deriving this carefully because it's not usually explained in books, and it's just usually just written down as well. We have to write down the annihilation operators to the right of the creation operators, but actually the reason is very physical. And so this sort of renormalization, as it were, of the 0-point energy is actually very natural. Okay, well, if there's no questions, then I'm going to go on to the actual calculation, and actually this is what we've just done is a conceptually interesting part of this, just setting it up. So now we're going to talk about Bose-Einstein condensation. So what we're going to do is what our goal is we want to do an expansion in the interaction strength. And so before we go ahead and do that, we ought to go and find out what happens what happens without any interactions. So that's our goal. I want to let me do this, and then if I forget to do this, somebody please remind me. I want to go back and talk about this particular form of the energy. So let me first of all look at what happens when there's no interactions. So we're going to set what just happened. Okay, let's try again. So what we're going to do is we're going to set u equals 0 just for now, and then we expect Bose-Einstein condensation into the ground state. And the ground state is the state with 0 kinetic energy, and so K is equal to 0. So what we expect then is that the number of particles in the ground state of the system, I'll call that A0 dagger A0, that is going to equal the total number of particles in the system, N. And then if I look at the number of particles in a state with wave number K, then that's going to be 0 for K not equal to 0. Okay, so that's the ground state, and so what we're going to do is the basic idea of what we want is that when U is not equal to 0, that something similar persists.
Sorry, can you clarify what you mean by 0 ket and K ket? And
so that ket means the vacuum.
0 ket.
Yeah.
Okay. And then in that bottom equation,
so AK dagger AK creates a from the vacuum a state with K with N K particles in the K in momentum state K.
Okay. So is that ket on the right-hand side of the bottom equation? Should that be K, or is that still a vacuum ket on that bottom equation?
That's also no. It's correct as written.
Okay. Okay.
Okay. So let's now. So now I want to make a very important comment, and we're going to talk about the pseudo-potential approximation. So the pseudo-potential approximation is this. We are going to make a simplification. So let me just tell you what it is. The approximation is we take the Fourier transform of the pair potential, which over here on the left-hand side, you can see comes in as a function of UK1 minus K3 in the way I defined my K variables. And we're going to say that this thing is equal to a constant independent of K. Okay, so that's called the pseudo-potential approximation. So what that means in real space is the following. What we're replacing is that U pair potential as a function of R, we're replacing that by U naught times delta of R. So what we're saying, the logic is, what we're saying is that the particles interact at very short range. They have hardcore repulsions, and so we're going to say that that hardcore repulsion is basically the main thing. And so you can think of it like this. Here are the two particles coming together. Like so, they collide. And if I look in the center of mass frame for those particles, so what I have here is R, here is the potential energy. So that we expect to look something like this. So that's what the potential energy looks like. And what do we expect the wave functions to look like? Well, what we expect the wave functions to look like is that over here, they're going to be some sort of plane wave, and then over here, something like this. And the picture that we are going to try to have in our minds is that we're going to be looking far away. And so this area here, this part of of space is going to be compressed down to 0. In other words, we can't really see what is happening there. So imagine that I've got my point particles colliding together, but I'm only looking at it from far away. So even though these are not points, they have some characteristic scale, something like that. What you can say is that when you look at these from far away, that they behave like point particles. And then if they behave like point particles, then you might want to know, okay, well, what is the effective interaction between point particles? And those of you who came to the course last quarter will say, okay, well, it's obvious what we do there. We're looking on larger and larger length scales. We can't resolve the smaller distance scales. We integrate those things out. And so the normalization group will tell us the answer to this question. So indeed, it would. But what we would expect is that therefore there'll be an interaction. So U of R minus R prime should be proportional to delta of R minus R prime, because there's nothing else it can be if they're point particles. and then the constant of proportionality. So U of R equals U naught delta of R. This thing here must encode something to do with the scattering process. So if it encodes details of the scattering process, then you want to ask yourself, well, which details does it encode? And the point is that far away from the scattering event, you just see point particles colliding. And so then all you see is the S wave scattering. And so when you work out the Born approximation for the scattering theory, which I'm not going to derive for you, so Born approximation for quantum scattering. So it's a Feynman diagram calculation of the scattering in perturbation theory. What you derive is that U naught is equal to M. Sorry, not U naught. U naught is equal to 4 pi h bar squared over n times A. And A, I've drawn it there, is kind of like the particle radius or diameter or something like this. So, but this is technically the S wave scattering length. So if you're not used to this and don't really fully understand it, that's fine. Most people do not. The calculation of scattering theory is quite an advanced topic, and it is very subtle. So the main thing that you should see as fairly natural is the idea that we're looking at these point particles colliding at very large length scales. So the interaction potential is effectively going to be just at one point. So it's going to be a delta function. There should be a relationship between the magnitude of the potential, the U naught, with the size of the particles, and then a detailed scattering theory tells you that it looks like the form that I've put in the box there. So any questions about the pseudo-potential approximation before I go on?
One quick question I had, just to relate this back to ideas from RG. So A in this case is like roughly like the size of the point particles, or like the S wave scattering length here. So in our limit, we're thinking about it as asymptotics. We're saying that A over some coarse graining length scale is going to 0. So we're sort of thinking about A in some dimensionless sense is going to 0. However, A still shows up in U naught here. So can we think of this as an example of scale interference?
It's really a statement of phenomenology. It's not really scale interference. It's simply that if I'm looking at long distances, the potential, the scale of potential has to come into the calculation somehow.
Okay.
So I think Mustafa had a question in the chat or comment. Isn't the distance from 0 to the local minimum? Isn't it? Yes, that's right. So you can think of A as roughly being the distance. Yeah, I'm drawing it on the left-hand side. So it's something like that, but it's not precisely that. It's more like this, more like the hardcore radius. but it's not really that either. So you have to sort of calculate precisely. But it's something of that order, that some scale relevant to the actual physical potential has to come into this description of the system. That's
Okay.
exactly.
So it's
Okay.
not necessarily scale interference. It just is that it has to encode something about
There's no anomalous dimensions and so on in
I
this,
see.
at
I
least
see.
in the way that we're talking about it.
Okay, thank you.
Okay, yep, no problem. All right, so now we're ready to do a calculation. So that's the end of talking about the pseudo potential approximation. So I just want to say, for further reading about the pseudo potential approximation, please look in Teams, and I posted an article I wrote for a book called 50 Years of Renormalization Group. And so I posted that on Teams. Okay, so now back to our calculation. So what we saw was that the idea of Bose-Einstein condensation is that we have a macroscopic number of particles in the ground state when there's no interactions. So now we're going to assume. So the next thing we're going to do is we're going to now switch on this U naught, so we're going to say it's non-zero rather than zero, and then we're going to say that the occupation of the ground state is n naught, and n naught is less than the total number of particles in the system. Now, why do we think that? Well, the excitations are going to raise the energy of the system, so the interactions may push some particles to excited states. And in fact, we're going to see that we're going to allow for that possibility. And in fact, we're going to see that is exactly what happens. So let's see how we're going to do this calculation. So the basic idea behind this calculation is that the annihilation and creation operators for the ground state are effectively classical variables, and the annihilation and creation operators for excited states are quantum, and so do not commute. So that's the basic idea. So how do we carry that out? So what we're going to do is we're going to find some new variables. The ground state operators. So I'm going to define A naught dagger to be the square root of n times B naught dagger. So I have to find some B naught, and A naught is the square root of n times b naught without the dagger. So why do I do that? Well, then if I look at the commutator of b naught and b naught dagger, that is going to equal 1 over n times something. And so it's basically going to be 0 as I take the limit n goes to infinity. So that means that they essentially commute. Implies that they are classical. So isn't that funny? We have a system which is quantum mechanical. We're looking at the macroscopic occupation of a quantum state. And because of that macroscopic occupation, there's a large number of particles in that ground state. And therefore, that quantum ground state can be treated can be treated classically. Okay, so it's it's a very paradoxical statement. Okay, so if that's the case, then what we're going to say is that that A naught and A naught dagger, we're going to replace them just to make sure that you realize that they're classical. We're going to replace them by a variable called A naught dagger, and that's just a complex number, and that's a number that is of order the square root of n, like so. And so then what I should get, scrolling through my notes here because I think there's a typo. So what we should get then is that if I write down what the field operator is, so the field operator, if you remember what the field operators were, so those were simply going way back to the beginning here. The field operator created a particle at the point r in space, or destroyed a particle at the point r in space. So those are the sum over k modes. You can see them here on the left at the top of the screen. And what's going to happen is when we do that sum over k, we're now going to separate out the k equals 0 mode separately. So what's going to happen is that we're going to have this. It's going to look like A naught over the square root of v plus 1 over the square root of v, the sum over k not equal to 0 of e to the I k dot r times ak. And the same thing for the psi. So what we've done is we've taken that definition over there on the left-hand side, and we have separated out the k equals 0 part, and the operator is going to look like that. Okay, so this has important consequences, and everything we're going to do next is going to be the algebraic consequence of having made this separation between the classical and quantum degrees of freedom. So let's suppose I then ask, well, what is the number operator? Well, the number operator was psi squared, so that's going to look like A naught squared plus the sum over k not equal to 0 of a k dagger ak. Okay, so that's what the number operator looks like, and this A naught squared, this is equal to the number of particles in the ground state of the system, and the other term over here, this is equal to the number of particles that are in excited states. Okay, so that's the basic idea. So now what is the strategy? So here's the calculation that I'm going to do now. What we're going to do is we're going to say that because we have a macroscopically occupied state, in some sense, if I look at the measure of, say, the annihilation and creation operators, they are much smaller than the complex numbers that define the ground state of the system. So over here, these A naught, this is just a complex number. It's not an operator. So now what we're going to say is, if A naught is small with respect to A naught, then that implies, let's try to do perturbation theory. In the AKs with K not equal to 0. And another way to say that is we're doing perturbation theory in the expansion parameter U. So now what we're going to do is perturbation theory. And this is where the algebra gets a little bit messy. So just want to warn you about that, but just sort of follow along with the calculation, which I'll do all the dirty work. All right. So now, if you're following in my written notes, this is section 3.4.4, and what we're going to compute now is the excitation spectrum. So we're going to end up deriving the quasi-particle form. So what we're going to do in this section is we're going to derive the quasi-particle picture. And there's going to be a bunch of steps, and they're really boring, so you can go to sleep, but I'm going to wake you up when we get to the interesting ones. Because the interesting one here is it's really fantastic, it's really powerful, and it's quite a brilliant idea. So let's go through with this. So some very interesting steps along the way. All right, so let's do step one. Step one is not terribly interesting, but we have to do it. When we look at our Hamiltonian, scooting back here to the Hamiltonian written there at the top of the page, every term in that sum is a sum over k of AK daggers and AKs and things like that. So the fundamental object that we are going to need is this sum over k AK, and that's the main thing that we're going to need. So we know that that is just going to be the sum over the 0th mode, which is A naught, and then the sum over k not equal to 0 of AK. So that's what we mean by the sum. So now we're going to use this, plug into the Hamiltonian. Okay, so let me do that for you. So I'm just going to write it down. I'm not going to talk while I write it because I'll make a mistake. Okay, so what I've written down is what the Hamiltonian looks like, and I've included terms that start off as a constant. So there's a constant term over here. Then there is terms that are quadratic in AK and AK daggers, and those are the ones in white and blue. And then there's terms of order A cubed, and we're going to neglect those. So we're only expanding up to second order. And the reason we're only expanding up to second order is because actually all we want to do is all we want to do is try to turn this thing into a free particle Hamiltonian. So we only go to order A cubed because ultimately drive a quasi-particle, i.e. non-interacting picture of this many-body system. Okay, so that's good. So now let's carry on. So that's all well and good. Now what we want to do is the next thing we want to do is express in terms of the total number of particles, and so get rid of A naught. So A naught was just the number of particles in the condensate. That's related by this formula over here, which I'm just outlining it in yellow on the left-hand side. So we're going to now substitute for A naught what that thing is over there. So let me go ahead and do that. So then what I end up with is the following: H is equal to U naught n squared over 2v plus the sum over k not equal to 0, h bar squared k squared over 2m, ak dagger ak, and then the interaction term u naught n over 2v, a k dagger a minus k dagger plus a k a minus k plus 2 ak dagger ak. So that's what you get, plus order a cubed. Okay, so that's already quite interesting, because if we just look at this term over here, so this term already tells us that we have a ground state energy which looks like this. Now, if there's no excited states at all, we'll call it E naught. That's going to be n squared U naught over 2v. So this is the ground state energy. In other words, if there was no occupation of k not equal to 0. Okay, and if I were to work out the chemical, mu is d E naught by dn. That's going to equal the number of particles in the system times U naught, where n is the number of particles per unit volume. Okay, so that's step one. Now let's do step two. And so step two is to use a little trick. Okay, this trick is helpful. So the trick is this. If I take the sum over k of some function of k, I can write this as the half the sum over k of f of k plus 1/2 the sum over k of f of minus k. All I'm doing is I'm summing over k space twice, and but calling the dummy variable minus k. So that's an identity. So therefore, I can write that the total number of particles in the system is the number of particles in the ground state, and I can write it in this way, plus 1/2 k not equal to 0 of a dagger ak plus a of minus k dagger a of minus k. So all I've done is I've added and divided by 2 the states with momenta minus k to the states with momenta k. Now, why I've done that, it's just a technical trick, as you'll see, but it's a very convenient one. So then if I do this, then now what my Hamiltonian becomes is the following. It's 1/2 u naught times n, and then 1/2 the sum over k not equal to 0 of h bar squared k squared over 2m plus n u naught times the number operator ak dagger ak plus a minus k dagger a minus k. So that's just the number operator written down in this way where I've added in the states explicitly with minus k. And then there's another term, which is the interaction term, another interaction term, which is 1/2 the sum over k not equal to 0 of n u naught times ak dagger a minus k dagger plus a k a minus k plus order cubes. Okay, so that is the Hamiltonian to quadratic order, and it looks like a mess. It looks like a mess because it's got sort of these terms that we don't really understand. Now, the terms that we don't really understand are these ones. We don't know what those really mean. These ones over here, these terms, this is just the number operator. So those are fine. We're quite happy with those. But the ones that look like a dagger, we've never seen those before. So what we want to do now is if we're going to write this Hamiltonian as a sum of independent particles, well, that means that it's going to be diagonal in k space. So what we actually want now is we want to diagonalize this Hamiltonian. That's our goal. And I'm going to show you how we diagonalize them. So this is the trick. We're going to define new variables. We're nearly finished for today's lecture. We're going to define some new variables, alphas, which look like this. uk, ak, plus vk, a minus k. And then alpha k dagger is equal to uk, a k dagger, plus vk, a minus k dagger. So those are some new operators. Okay, now why do we write these things down? Well, what's going to happen is we're going to assume that the uk and vk are real and spherically symmetrical. In K, and we're going to determine them. We will figure out what they have to be based on 2 physical constraints. And these physical constraints are really, really important. Now, I've written down these alphas. We don't know what they are. They're just some operators. And what we're going to, but you know, we have the Hamiltonian in terms of the AKs. So we will calculate H in terms of the alpha Ks. Okay, that's what we're going to do. And so to do this, we need to express the A's in terms of the alphas. Okay, so let's do that, and then we'll finish for today. So if we take the equations on the left hand side, if we multiply the top one by v, so let's call this equation. This is actually equation 3.110, and this is equation 3.111 in my notes. So let's take VK times equation 3.110 and UK times equation 3.111. Okay, so if I do that, then I get the following: VK alpha K dagger is equal to VK UK AK dagger plus VK squared A of minus K. And similarly, I get UK alpha K, sorry, alpha of minus K is equal to UK squared AK plus UK VK A of minus K dagger. And I just want to check that there isn't a typo in my printed notes. Okay, I think this is right. So I'm going to subtract these two things. So I think there's a minus. I think there's a minus. Well, yeah, no, this is fine. So if I subtract them, there is a typo in my printed notes, I believe. And what I get is VK alpha K dagger minus UK alpha of minus K is equal to minus UK squared minus VK squared A minus K. And if I insist that UK squared minus VK squared is equal to 1, then what I get is that alpha, what I get is that AK is equal to UK alpha K minus VK alpha minus K dagger, and AK dagger is equal to UK alpha K dagger minus VK alpha minus K. And that's where I'm going to leave it for today. So, what we've found is a condition if we assume that this is true, then we can invert this transformation and express the A's in terms of alphas. Okay, so what does this mean? What this means is the next step, which we're not going to do today, of course, is to then substitute this form for A into our Hamiltonian on the left-hand side and express it in terms of these alpha variables. Now, what do these alphas correspond to? What you're going to see next time is that these turn out to be annihilation and creation operators for new particles, and those new particles are the quasi-particles. And we're going to see that explicitly after we've applied one more condition. Okay, so that's where we'll leave it. Does anybody have any questions before we quit for today?
Well, one quick question I had. So we went into this that saying the approximation we're making is that this is weakly interacting. Mathematically, I feel like we made two approximations. One was in the form of the potential energy, and then the other was treating the A0 creation operators as classical. Which of those mathematical approximations corresponds to this sort of physical idea of weak approximations, or is it both are important to encode this idea of weak interactions?
So the fact that most of the condensation is in the ground state is where the weakness occurs.
I see. Because
Okay.
it's like the energy scale is going to be of order the number of excitations, and that's just going to be much smaller than the energy scale of the ground state.
Well, that's one way to say it. But what we're saying is that if the interactions were really strong, then I would think that many particles would be excited out of the ground state and would not be in the excited states. And in fact, that is actually true. So if you look at superfluid helium, you find that only roughly 10% of the particles are actually in the ground state because it's strongly interacting. Whereas in an atomic Bose-Einstein condensate, cold atom, it's much higher fraction of particles are in the ground state. So that's really the ultimate measure of the interaction strength.
I see. Okay, thank you.
The pseudo-potential approximation is a very, very subtle one, and you want to look at my article about the normalization group to understand that, or at least get some insight. Any other questions? Okay, so let me just stop the recording.